Okay, so hello everyone and good afternoon. Welcome to the second session of the course on programming languages, semantics and verification. So let me start by asking you if you have any questions about the material that we covered. Okay, great. I take it as no one has any questions. Uh, so let me just share my screen and start. Okay, so in the last session, we talked about the while programming language and we went through its operational semantics. So in this session, we are going to continue with that. We're going to see another flavor of operational semantics, which is called big step operational semantics. And we are, of course, also going to uh, see some use cases of the operational semantics. I will show you a concrete example of how you can use operational semantics to verify the correctness of a program. Then, if we have time, but this would probably be the next session, we will go to denotational semantics. So let me start by one rule that we discussed in the previous session, and this was when we were working on the simple while programming language, which is the same language that we're going to work with today. So this is the syntax of our language. So we wrote this rule for while, and we said that this doesn't really work. And the reason that it doesn't work is that it will just cause non-termination. And basically, we could see this even syntactically from the fact that we never get rid of the while. Okay, so, but what was our intent when we were trying to write such a rule? The intent was to write a rule for the while condition, for the while loop, without actually having to break it down into two cases, the case where the while guard B holds and the case where it doesn't hold. So we saw that this rule doesn't work, but a nice question would be what kind of rule would work? And here's an example of a rule that actually works. So if instead of rewriting the while using an if like this, you rewrite it like this. So the main difference here is that in the wrong rule, we first executed an if and then executed the while. But here we are putting the while itself inside the then part of the if. Okay. Oh, this shouldn't be do, it should be then. Sorry about that. Okay. So why does this rule work?
Because the while line only executes when the if condition is true, and
Right.
if B is not true, then nothing happens. We just skip that.
Yes. So basically, and the problem that we said doesn't happen anymore because uh, if B is false here and we are trying to execute this, then we will get rid of the while eventually. Okay. So, oh, by the way, I'm really bad at multitasking, so I'm not looking at the chat at all. If you want to say something, please say it. Unmute yourself and say. Okay. So, uh, this was the only thing that I wanted to say about this uh, small step operational semantics that we had. But now let's just go one step further and let's make this even nicer actually before going. So uh, I can rewrite this rule, right? So I can take this thing, put it up here, and say that if from here you can transition to something like p val prime, then you can do the same transition from here. So this can also alternatively be a while rule for us. Okay. Uh, so uh, because it's interfering. I guess I can do nothing about it. So now that we have our transition relation, which we showed with this arrow, we can also define the transitive closure of our transition relation. So the idea of the transition relation itself was that from one state, you can go to another state in a single transition. But when we get the transitive closure, it captures the fact that you can go from this state, p val, to some other state, so p prime val prime. But okay, no, okay. But probably with several steps of execution. So not just one, maybe zero, maybe more than one. And these are basically the rules that we can have for this new relation, which is often called either the transitive closure of the transition relation or just the reachability relation. So when I write something like this, I mean that from this state, I can reach this state with probably several different transitions. And the definition itself is, of course, very easy. So from a state, you can definitely reach itself. And if you can go from one state to some other state, and then from that other state, you can reach a third state, then you can reach the third state from the very first state. That's also obvious. And then using these definitions, these rules as the definitions of the reachability relation, we can basically define some redundant rules as well. So uh, these are lemmas that can be obtained from the original definition. But even though these are lemmas, they are useful. So, and what they say is pretty obvious. So if you can, it's basically different combinations of multi-step reachability and single-step reachability, and all of them leads to multi-step reachability. Okay. So this is all I wanted to say uh, about our small step operational semantics. But let's now move on. Okay. One thing that we actually used quite a lot in defining the rules of our semantics was this kind of thing here. We basically, well, the intuitive definition that I gave you was that this means the value of A. It means that you evaluate A. So I'm going to make that more precise now. So let's say that you have an expression, and your expression can either be an arithmetic expression. For example, in this case, A is an arithmetic expression defined by this grammar, or it can be a Boolean expression, which is defined by this other grammar. Now, what we want to do is that we want to actually assign meanings to these expressions, right? And before I said that when I write something like this, I mean uh, the, the result of evaluating the expression A according to the valuation val. So, for example, if A was x plus y, and in the valuation we had value 1 for x, and in the valuation we had value 2 for y, then this would be 3. But this doesn't really explain the weird syntax that we have here. And that weird syntax has a good reason. So basically, formally speaking, the meaning of A, or the semantics of A, which we write it like this, is actually itself a function. And this is a function that maps valuations to numbers. So in our case, because we only work with z, we say that it's in z. So we are only working with integers at the moment. So basically, this bracket A is a function from all the valuations to z. And how is it defined? Well, it's basically defined like this. Bracket A of a valuation is the result of putting everything, every value from that valuation, substituting it into the uh, variables in A, and it's actually the concrete value. But well, we have to define this much more formally. So what I said right now is very hand wavy. So let's do just that. Let's make this very formal. Okay. How do we make things formal? Well, until now, the only way that we have is to write rules. So we can write rules for the semantics of arithmetic expressions as well. So a simple rule at first would be, what is this? So if C is a constant expression, what is the meaning of C? What is the, uh, how should I define the semantic of C given a valuation? Well, this is of course simple. It's just C because it's a constant number. Right? The other case, which is also easy, is what happens if I have a variable. So if I have a variable X and I use this variable as an expression. So my expression is just X. And I want to evaluate it at val. Well, this is also very easy. It's just the value of X. So these are our two axioms. Now, how do we define other operations? So, for example, if I have summation, if I have A plus A prime, and I have it at val. Oh, and by the way, before continuing with this, adding these many parentheses is going to be quite hard. So I just drop many parentheses, and I expect you to understand what this means. It basically means that this is a function, this part, and okay, this part is a function, and I'm applying this function to this value. Well, the value itself is again a function, but in this case, it's just an argument that is passed to this function. Okay, so how do you define this? The valuation of a plus a prime in val. Can you write a rule for this? So you can try writing it in the chat. So basically what I want to do is that I want to give a formal definition for evaluating a plus a prime given a valuation val. Right, that's fine. But we don't want to do it like that right now because what you've written is actually more in the spirit of denotation on semantics, which we will see very soon. But what I'm going to write is basically equivalent to that. So, no, so you can't write val of a plus val of a prime because a and a prime are expressions. And so let's just write the types. Val is a function from variables to z, right? So when I write val of x, this makes sense because x is a variable. But I can't write val of a because a is an arbitrary expression and it might not be a variable. Yes, okay. So this last one is actually correct. So we can write it like this. If the valuation of a, if the meaning of a or semantics of a is b, and if the semantics of a prime is b prime, or maybe let's just use c because we want to show that it's a concrete value, then this would be c plus c prime. And you can write the exact same thing for all the other operators as well. So you can write the same thing for multiplication. You can write the same thing for everything else. But well, the mode operator is a bit trickier. So let's do that. So how do you define the mode operator? So again, let's say that we have these assumptions that the evaluations of A and A prime are C and C prime. So how do we define the mode operator? Yes, there are several special things about this here. So one important point is that we cannot divide by zero. So division by zero is always problematic. And for that, we have to basically put a side condition saying that C prime is not zero. Okay. But other than that, we have to also give a formal definition of mode. And this is easy. If C is KC prime plus D and D is less than C prime, then this would be right. Okay, so this is the definition of arithmetic expressions. And once again, just pay a lot of attention to the types. So evaluation maps variables to concrete values, and then the semantics of some expression A maps what to what? It maps valuations themselves also to concrete values. Okay. So we are already working with higher order functions, and this is something that people in functional programming really like. Okay, let's go on. So what should we do for Boolean expressions? So let's first ask about the type. So if B is a Boolean expression, what is the type of the semantic of B? What is the meaning of B?
Its output is either true or false.
Right, but what is its domain then? So it's a function and the output is only either true or false. But what is mapped to true or false?
It can depend on the situation.
So actually, well, it's very similar to before. It just maps a valuation to true or false. But there is still a really stupid problem here. And the problem is that what happens if one of the arithmetic expressions that are used in this Boolean expression are not defined? So for example, if you have division by zero, then this Boolean expression itself should also not be defined. So this type would actually not be exactly a function, but a partial function. So it maps some of the valuations to true and false, and then it's undefined for the others. You can also change this to true, false, and error. That's also okay. But we want to keep the undefined thing there. So, and here as well, if it has division by 0 or some other error like that, we just assume that the meaning of A is undefined. Okay. So let's write the rules for Boolean expressions now. Let's start with the simplest case. What are the rules for true and false? So actually, these are going to be axioms. Can you give me the axiom for true? Yes, exactly. But yeah, there shouldn't be an arrow there. You should use the equality sign because the arrow, we only use it for transitions. Yes. So true is always true. And the same goes for false. So I'm not going to write that. So now let's try the meaning of A greater than A prime. And A and A prime are both arithmetic expressions. So we can do this with a basic side condition. So if the meaning of A is B and the meaning of A prime is B prime, and if B is bigger than B prime, then this would be true. If B is not bigger than B prime, then this would be false. So we will have two rules only for this one comparison. And then we will also write similar rules for all the other comparisons. Okay, let's do logical operators. So how do you do B or B prime, where B and B prime are Boolean expressions right now? So these are Boolean expressions, and we want to evaluate them at a given valuation. Okay, can you write them in the chat? Give me one rule at least. So let's start with the simplest case. What happens if B itself evaluates to true? So if B evaluates to true, then of course B or B prime should also evaluate to true. And the same thing goes also with B prime. So if B prime evaluates to true, then B or B prime evaluates to true. But we also need just one more case, and that's the case where they're both false. So if they both evaluate to false, so B prime is false, and B is also false, then B or B prime would be false. And then we can do the same thing for and for not. So
I
the
have a
reason I
question.
did, yes.
I have a question. What if B prime evaluates to true, but there is a failure when you evaluate B? Then
Yes. So
maybe
basically, we are catching failures, but by not having any rules, right? So when you don't have a rule that assigns a value to something, it means that it has failed, and then the value is undefined. So if one of these is undefined, then I don't have any rules that uses that. So B or B prime would also be undefined. right? So this is how we basically tackle the errors.
Sorry, I have a question.
Sure.
So I want to ask, how do you infer what operators are available in the precondition? Like I see that we are allowed to use like b bigger than b prime in the second rule, but in the fourth rule we can't use the or operator. So when do we infer
Well,
which rules are available to us?
basically the rules are defining your semantics in terms of an underlying logic, and it really depends on what underlying logic you're using. So I'm just using basic first order logic. So you can use or as well.
So it really depends on the person who created language to determine what kind of operators can be
Yes.
used in the precondition.
So
Is that
basically the rules are defining this language in terms of some other language, right?
yeah.
And the logical language or the mathematical language that you're using. And you can use any operator that you think is well defined in that language.
Okay, thank you.
Okay.
So,
But
excuse
the
me.
reason I did this is because I wanted to really be able to handle all these cases with undefined and talk about that.
Excuse me.
Sure.
Yeah. Like I would like to ask, like, say, so, like, I mean, the way we are now defining these or, Boolean expressions, can it reflect the shortcut like situations when execution? Like,
Yes. So that's the thing. What we are doing here is that we are just assigning values, right? And
yes.
it's kind of like a double shortcut, double short circuit, because I also have this rule which says that just evaluate p prime, and if
Yeah.
p prime was fine, if p prime was true, you take this to be true.
Okay. So like, I
Right.
mean, like
So
the way we are now defining the semantics implies that like
yes,
our language will have shortcut behaviors.
yes, and on both sides too.
Okay.
So if you want to have the
okay.
behavior of, for example, C++, which has short circuiting only on one side, then you will have this rule which says that if the
Oh.
first one evaluated to true, you don't care about the second one. But then you will not have the other rule. Instead, you will have something like this. If the first one evaluated to false, and then the
Okay.
second one evaluated to true, then
Okay.
you have it. So yeah, basically how you write your rules changes a lot of things.
Okay, so the
But
preconditions also reflects the way of execution.
yes, so
it's
the
not
rules, yeah, indirectly they do that because the rules define how things work, right?
okay.
So the rules define what it means when you say B or B prime.
Okay, thank you.
And actually, to make things easier, let's just get rid of these operations that can make undefined behavior. For now, we just make life easier, and then these functions will all be total functions instead of partial functions, and we don't have to define anything else. Okay. Yeah, and this one will also be a total function. Okay, so
sorry, I have a question.
yes.
To define the semantic of this expression, should we need add another rule to define it? Because here we have two rules, and when the expression B is evaluated to true, then the disjunction should be evaluated to true, but it is locked in this slide.
Yes, you need more rules, but what I was doing here was just trying to show you how you can write the rules. I don't want to write all of them. So if you want to be completely sure, for example, you can write every single case, right? There are 4 cases, and you can have a rule for each one of them. Or you can have short circuiting and write rules for 3 of them instead of all 4 cases. And then merge 2 other cases in one. So as long as your rules specify everything that your program wants to do, it's fine. And these rules don't do that. So the reason behind doing this exercise was to just show you that you can define even the evaluation of expressions as rules. And this is in the spirit of operational semantics. Okay, so the next topic that I want to cover, and it's going to be quite similar to what we have already seen, is what we call big step semantics. This is also another flavor of operational semantics. So what we did in the last session was that we had this arrow which basically denoted a transition. And by transition, I intuitively meant one step of execution of the program. So when I had an arrow between two states, it just meant that the program can go in one tick from this state to that state. So this is why we call it small step. But now we can also define big step or large step semantics. This is also sometimes called natural semantics. And the idea here is that we just go all the way and see where we leave, where we terminate. So when I write this expression, what I mean by it is that if I start executing my program from this state, if I start executing P over the valuation val, it will terminate, and it will terminate in val prime. Okay. So again, we have to write rules. So the simplest cases are the cases of skip and assignment. In case of skip, there is really nothing special to write, because even in the small step, we just had that skip ends the program in one step. So you just change the direction of the arrow, that's all. And the same goes for an assignment. But let's see what we can do for sequential composition, while, and if. So can you write rules for big step semantics of sequential composition? So when can I say that, for example, PQ val, I need to copy that value, goes to, let's say, val prime. What should I write as the requirements of this rule? Any ideas? So we only have this new kind of arrow now, which denotes big step execution. So I can use that. Let's see what happens. Let's say that I execute P over val, and it ends up somewhere, let's say, val double prime, right? Then I have to, okay, let's put double prime here to make it nicer. Okay, then I have to write, to execute Q from the valuation that we had at the end of the execution of P, and see where it lands. So this is our rule. If you start from a valuation and run P and go to an intermediate valuation, and then from that intermediate valuation, you run Q and end up in another valuation, then you can basically just run P and Q from the initial valuation and end up at the final valuation. So this wasn't too hard. Okay, what can we do for if? So again, we have this casework that we always have. So if I want to write a rule for if P, then P else Q, and if I want to start from evaluation val, Okay, where would I land? So let's first say that B evaluates to true. And now you really know what this side condition means. So if B evaluates to true, where should I go from here? Okay, so let's say that if I run P from val, it terminates in val prime, then this will also terminate in val prime. Right, okay. And the false case is also very similar. We just copy these things. And if it's false, the only difference is that you have to do what Q does. So you put Q here. This is false. Okay, now we get to the interesting part. The interesting part is what happens with while. So we can write a bunch of different rules for while. While B, P, and we're starting from evaluation. Okay, it becomes hard to read the chassis. Okay, so one thing we can do is that we can do the casework again and say what happens if the while condition is true and what happens if the while condition is false. But can we do it without that? So let's do it first and then we come back and talk about this. So if the guard holds at the current valuation, then we know that we should do P, and then after that we should do the while again. So we basically say that we can do P and then do the while. And if from here you go to val prime, like that, then here you will also go to the same place, val. So the idea is that if the while guard is true, then I have to run one iteration of the while, and then I have to run the while all over again. So I can just see where that lands me. For example, if it lands me at val prime, then I will also land at val prime. And the other case is much easier. So what happens if this is false? Yes. If this is false, then the while doesn't do anything and it just terminates, and you're terminating at the same valuation that you were before. Okay. So these are the big step semantics now. So what do you think are the main differences between this kind of semantics and the small step semantics? So one thing that you would see right away is that in small step semantics, we really captured all the possible transitions of the program. But here we don't have that. Here we basically only have these down arrows that immediately end the execution of the program. And what this means is that if you have an initial state and the program does not terminate from that initial state, then you will have nothing about it here, right? So the big step semantics only give you information about those states that actually terminate and tell you where they terminate, with what valuation they terminate. And for the other states, all you know is just that the program will not terminate from this state, but nothing more. Okay, so let's take another look at our while rule here. So at the beginning of this session, we wrote a new while rule for the small step semantics, and it was this. So can I write the same rule for big step? Can I just change these arrows to down arrows? Okay, how many people say no? Write no in the chat if you say no. Okay. Yeah, and write yes if you think yes. Okay, we have yes question mark. Okay, people who say no, why do you think no?
I think because you cannot execute to the middle of the program, you have to give a whole answer, but the precondition part is a larger program, so it will not output any answer.
Okay, people who say yes, what's your answer to this? Why is this not a problem?
Basically, I didn't see anything wrong if we change this arrow to the down arrow.
Yes, so yeah, I'm just changing this to a down arrow, let's say. Yeah. So the problem that the no people have is that this program here is larger than the original program down here. But that doesn't really matter. And the reason is that there are basically two cases. Either this while down here is going to terminate, or it's not going to terminate. If it's not going to terminate, this is fine. Well, our rules don't terminate either, so that's fine. You don't find any proof that this terminates. It's okay. But if it actually terminates, then the number of iterations would be finite, right? So let's say it will terminate in n different, after n iterations. So in that case, we will make this program bigger and bigger, but we only do that n times. And then at some point, we will make it smaller, right? So first I make it bigger, then I run the if part, then again, I'm back at the same program with a different valuation. I make it bigger again, I run the if part, and this goes on for n steps. But then at some point, this if condition would be false, and then there it terminates. So there is no problem with this. This is a fine rule. You can use this rule. Okay. Let's just put the slides back in the original position. So now we know about big step and small step, and we know about how we do evaluation. So finally, the question is, what is all this good for? What can we do? So here's the very first example of a verification that I want to show you in this class. So let's say that you have a program and you want to prove that the program terminates. Well, the very first thing that you have to do is that you have to specify what you mean by the program terminates. So we define termination, and there can be different definitions for this. So this is the definition that you can give using big step semantics. Basically, if it ends at any valuation val prime, then it terminates. So term p val denotes that the program P terminates when it starts on evaluation val. Or you can give a definition based on small step semantics and this transitive reachability relation. So this is also the same thing. So what this says is that if you have a series of transitions, and with that series of transitions you get to a point where you don't have a program anymore, then you have terminated. So you can use these two as definitions of termination. And let's say that I use the second one for now. Now let's see how we can formally prove and verify that a given program terminates. So, before that, I have to say something about this. So a curious point here is that when we are defining termination, we are defining it for a program and valuation pair. So we are defining it on a state. So what I'm showing here is that, well, term of p-val means that the program P, when it starts on valuation val, will terminate. But what we are really more interested in, especially when we are doing verification, is to prove that a given program terminates on all initial valuations. So we are going to use these formal definitions of termination together with our formal semantics to prove that a given program terminates on all initial values. And the program that we are going to prove this for is basically the same program that we saw in the previous session, which is this Euclidean algorithm for computing greatest common divisor. Okay, so just looking at this program, can you give me an informal argument why it terminates?
X and Y has a lower bound in the execution of the loop, but X and Y also is also decrease in each iteration, so it is monotonic. So the loop must terminate.
Right, that's exactly correct. So now what we want to do is to write a proof that can be actually checked by a machine, or basically use our formal semantics to write the most formal possible proof for this. And this is interesting for two reasons. The first reason is that if a human writes such a proof, which is actually quite hard, then a machine can check it. So you can actually write proofs of correctness for your programs and have your compiler check it. And the second thing is that having these formal semantics actually allows some programs and tools such as, for example, Coq or Isabelle, which are called proof assistants or theorem provers, to actually find a proof. But now I'm going to show you what a proof looks like. Okay, so we do a proof by casework, and we look at the initial valuation val. So what we want to say is that we want to prove that for every initial valuation val, this program terminates. And the way we do that is basically a casework on the values of X and Y in the initial valuation. So the simplest case is if the while condition does not hold. If the while condition does not hold, then of course the program terminates. But how can we prove that? Well, so again, this is two cases for itself. One case is if the value of X is less than or equal to 0. And the other case is if the value of Y is less than or equal to 0, but they're very similar. So I'm just going to go through case one. And you will see that we are applying a lot of different rules, both from the evaluation rules and also from the small step semantics. Okay, so we start with this assumption. We know that the value of X in the initial valuation is less than or equal to 0. So the very first step is to go from this arithmetic expression to a Boolean expression. So this is the rule for comparison. And basically by applying the rule for comparison here, we get this. We now know that the evaluation of this Boolean expression is false, okay, at the given valuation. Okay, and then which rule am I applying here? So how do I go from this to this? Yes, it's the Boolean AND rule, but it's actually the short circuit version, right? Because we have this, we are only looking at the first component. So it's the short circuit version of the Boolean AND rule. And from that, we get this, okay? Then what I'm saying is that intuitively, because this condition here is false, then if I have a program which is of this form, if x is greater than 0 and y is also greater than 0, then, and then the if and while, when I put 3 dots, I mean the if and while in the original program. So this is the while that I'm talking about, and this is the if that I'm talking about. So whenever I'm talking about another if, I will actually write down that if. Okay. So here, which rule was used to go from here to here? No, this is not the while loop rule. So yes, that's the if rule, exactly. So here in this program, and you have to get used to reading these flattened versions of programs, the while is actually inside the then part of the if. Okay. So we are applying the if rule. The if rule says that if the condition of the if evaluates to false, then you just don't have to do anything and you terminate at the current valuation. So this one here is the if rule. Now the next one is the while rule that we saw today. So the while rule that we saw today was saying that if you have a while, you can basically rewrite it like this. And if from there you can have a transition, then if you can basically have a transition from this state, you can have the same transition from this state. And again, when I say while and 3 dots, I mean the original while in the program. Okay, so this is the while rule. Okay, so which rule did I apply here? So I'm just adding this star. So this is one of the rules that was in the definition of transitive closure, yes. And finally, what rule am I applying here? Yes, this is the definition of termination. So you see how this works. You can basically stack these rules on top of each other, and this whole thing is called a proof. So whenever I tell you I want a formal proof for something, this is what I want. Okay. And these kinds of formal proofs are just too formal. Maybe for humans, you don't need these, but for machines, it's actually easier to work with these kinds of rules and these kinds of proofs. Okay, so we went through 2 of the cases. Let's do the final case. And the final case is when both values are greater than 0. And in this case, we of course need induction. So we define a new variable n, a new value n, and we set it to just be the value of x plus y. And then we do induction on n. Okay. So this is what we want to prove. So we want to prove for every n that if the value of x is greater than 0 and the value of y is greater than 0 and the value of x plus y is n, then the program basically terminates. This is the same as termination, right? The program can even reach a state where there is nothing else left to execute. Okay, so the base case is actually very trivial. So the base case is when n is 2, and in that case, you know that the value of x is 1 and the value of y is 1. So you just have a single execution of the program and you just execute it and say, okay, it ended. So the base case is quite obvious. Now we do another case analysis for larger n. And the case analysis that we do here is that we basically compare x and y, because this is what happens here in this if. So we take two cases, if x is greater than y or if x is less than or equal to y. And the cases are again similar, so I'm just going to go through one of them. And hold your breath and don't be afraid. This is the proof. Okay. So let's go through this proof actually. And this is now no longer a linear proof, it's a tree-like proof, as you can see. So what do we want to prove? We want to prove that this whole program, this whole while loop terminates. So basically what we want to prove is this, that from the original while loop with a given valuation val, we can reach some other valuation val prime. So, okay, let's define some notation. Let's say that I define val double prime as the result of applying this assignment to val. So that's how I define val double prime. And of course, because we have the assumption that both x and y are positive now, I know that the that the value of x plus y in this new valuation is actually smaller than their original value. So how does the proof work? Actually, reading these proofs is much easier from the bottom up. So what we want to prove intuitively is that this while loop, the original program, reaches a state where you only have a valuation and you don't have anything else to run. Okay. In order to do that, we can do two different things. First, we show that this program reaches some other program. With one transition, it can go to the format that we just saw in the while rule, which is if and while. And then we show that that program actually reaches termination. So, and then putting these two together with the transitive closure rule, we get to the termination of this. Okay, but now let's go through the proof for each side. Let's first do the left-hand side. So on the left-hand side, what I say is that, okay, the value of x is greater than 0, so x greater than 0 has a value of true, the same for y. So I know that this expression evaluates to true. And this expression is the while guard, right? And because this expression evaluates to true, then I have this. Which rule am I applying here and what am I doing exactly? Can someone say this? So which rule is this line? Yes, it's the if rule for the true side. So if I have a program which is of this format, and this format is basically the unrolling of the while loop. If x is greater than 0 and y is also greater than 0, then first do this if, and then do this whole while. Okay, if I have such a program, because I know that at this valuation val, this condition holds, then I know that I have to step into it. And stepping into it is basically running this part, right? The if and the while. So I have to do the if and the while from the valuation. So this is the if rule. Okay. And this one is one of the variants of the while loop. So we wrote many different rules for the while loop. And one of them was this, right? So if the expansion of the while loop like this can have a transition to another state, then the while loop itself can also have a transition to that same state. Is this clear? Okay. So now let's look at the right-hand side. What happens in the right-hand side? So I've actually tried to not write everything here. So I start with this, but actually you can do the evaluation tree as well. So I don't want to do the evaluation tree twice. So what I can say is that because x is greater than y, so if I run this if and then run this while, which is what I have here on evaluation, the if itself is only going to do the then part. So I can replace the if itself with the then part, which is this. So this is the if true rule, right? And then on the other hand, I have my assumption here that if I apply x equals to x minus y, I get to a new state val double prime. And so which rule am I applying here? So how do I get from this to this? Yes, this is the composition rule, exactly. If I only had this program, I would end up at val double prime. But now I have this program and also some while after it, the original while. So I will just have to run the while on val double prime. Okay, so now I get these two things. And what rule am I applying here? So can you tell me which rule this is? Yes, exactly. It's the transitive closure rule. Because I'm starting from a program and a state and going to another program and state. And then from that place, so this is the same as this one, I'm going to somewhere else. So I can just put them together and go from the very first one to the last one. And this is the transitive closure rule. Okay, and then on the other hand, I have this, which is my assumption that x plus y has a value that is less than n. And what rule am I using here? Yes, this is the induction hypothesis. And because of the induction hypothesis, I know that whenever in the initial valuation, which is val double prime here, x plus y is less than n, this whole thing would terminate. So this is the hypothesis, and because x plus y is now less than n in val double prime, I know that this thing terminates. Okay, and finally, I put these two together and get this one. Which rule is this? This is again the transitive closure rule, right? From here, I can go here, and then I can go there. So it's transitive closure. And one more application of transitive closure, and I get what I wanted. So what I really wanted you to see is that this is hard. So we just gave a complete formal proof of, not exactly complete, because we still have to write the things here for evaluation as well. But this is almost a whole proof for termination of this program. And as you see, it's really hard for humans to write it, and it's also hard for humans to follow it. We have to think about every step. But this is the kind of proof that a machine can easily check. So you can easily write an algorithm that gets all of your rules and also gets a proof and checks whether the proof is correct. And this is what we really need in formal verification. So we want to be able to say that our programs are formally correct in the sense that we wrote a proof, or we somehow had an algorithm that wrote a proof for us, and then we checked that proof and it was correct. And on this fundamental level with so much detail. Okay. So I hope you don't hate this class already, because this is the last time that you are going to see something like this. Everything that comes in the next sessions is going to be just pure algorithmic and much nicer than this. I just needed to show this to you. Okay, here's another use case. So at the very beginning of the previous session, I asked you something about code optimization. I asked you whether we can do an optimization and whether a specific optimization is correct or not. So as you might expect, again, in order to show that an optimization is correct, we need to have a formal definition of what correct means, just the same way that we had a formal definition of what terminating means. And we also need a proof, and the proof would also be something very similar to the previous slide. So I'm not going to go through the proof here, but give me some ideas about how we can formally define when two programs are equivalent. So let's say I have two programs, P and Q, and I am a compiler. I want to optimize P. I want to basically take P out of my program and put Q in place of it. When can I do this? So in terms of all the objects that we have defined until this point of the course, just give me some mathematical thing. They terminate at the same final state. Yes, that's okay, but we have to be even more specific. Okay, Ching Hong Mak is actually correct. Well, not exactly, not and. So it should be if and only if. So we have to say that, let me remove this. They are equivalent if for all valuations val and val prime, this happens. So if I start from P and val, I end up at val prime. If and only if, starting from Q and val, I end up at the same val prime. Okay. And note that I am doing this for all over both val and val prime. And this is something that I really intended to do. And the reason for this is that it also captures the cases where the programs do not terminate. So based on this definition, if P does not terminate, then Q cannot terminate either, and vice versa. And of course, I've forgotten the stars. So let's put the star there. And you can also define it in terms of big step semantics. Okay. So let me give you another brain teaser. Does this definition work also for non-deterministic programs? So what does this say for non-deterministic programs? Yes. So it basically doesn't say that you have to have exactly the same type of choices. What it says is that if the first program starting from this valuation has a number of choices, non-deterministic choices, that leads it to terminate in this other valuation, then the second program should also have that, and vice versa, right? But is this enough? Yes, our current syntax doesn't express that. So, but we had also a non-deterministic while language in the previous session. So let's say that we also have, this is actually independent of the syntax, right? What I'm saying is that suppose I have a language and I have defined the semantics for it. And now I am defining what it means for two programs to be semantically equivalent. So if my language doesn't have non-determinism, this definition works. But my question is, suppose that we have the same while language, but we also have non-deterministic choice in it. So in the syntax, I will also have something like this. It can be P star Q, where this star means non-deterministic choice. And I will just, let's put P here. Yes, so you see, the problem here is that we have equivalence in the sense that when they terminate, the choices that they have for termination are the same. So starting from a given valuation val, if you write down the set of all valuations that P can terminate in, and then you write the set of all valuations that Q can terminate in, you will have the same sets, right? I don't know what memory states means because we just have valuations here. The problem is again in case of non-termination. So suppose that I have two different programs, and let's say this is my program P, which basically does this, x equal to 1 and nothing else. And this is my program Q, which says while 1 is greater than 0, or maybe I can do something else. So let's say x is 0, while. So what I wanted to do is that, yeah, while x is not 1, you either increase x or keep it the same. So you have a non-deterministic choice between setting x to 1 or just skip it. Okay. So are these two programs equivalent? Can you put Q in place of P as a compiler, or can you put P in place of Q? So they are equivalent by this definition, right? But what I want to say is that this definition is not really good for non-deterministic programs. And the reason is that if you look at the program P, what it does is that it just sets x to 1 and terminates. So P always terminates. But if you look at program Q, there is also some non-terminating run. And the non-terminating run is that if it starts with setting x to 0 and then goes inside the while loop, and every iteration of the while loop, it just takes the second choice, goes through skip. So it will just loop around itself, right? So their behavior is kind of different in that P has to terminate, all runs of P terminate, but Q also has non-terminating runs. So in that sense, this kind of equivalence doesn't really work when you have non-determinism. And basically non-determinism is hard. Okay, so we are running out of time. I can just give you a short preview of the next session and then answer any questions that you might have. So in the next session, we're going to talk about denotational semantics, and that's a whole different way of defining semantics. And the idea there is that you just look at programs as functions from inputs to outputs and try to define these functions. So we don't talk about transitions anymore. But we'll get to that in the next session. So do you have any questions?
Yeah, I have a question about the homework. How do we hand in the homework to you? Do we just email you or?
Yes, you can email it to me, or you can email
Okay.
it to the TA.
Okay, thank you.
I have a question about the last slide. So basically, we can say that these two rules are not sufficient for saying that two programs are the same when non-determinism exists, right?
Right.
Okay. Because that they may have different state, the final states that are not the same, and so that makes them not going to, I mean, not being the same at the runtime.
Yes.
Okay, thank you.
And actually, you can have also finer definitions of what it means for two programs to be equivalent. So we are talking about code optimization here, but if we weren't talking about that, in some instances, for example, in security, you want to make sure that the runtime of the two codes are also the same, because you might have an attacker that is monitoring the runtime and based on that can deduce something about the code. So you can define it any way you want. All I was saying here is that this kind of definition works really perfectly for deterministic programs, but then it runs into some errors with non-deterministic ones.
Okay.
Oh, and actually another thing that I just remembered here is that this is not just about code optimization, it's also about compilation. So think about what it means to compile a program. You basically have a source language and you have a target language. So your source language might be, for example, C++, and your target language is, I don't know, x86 or some sort of assembly. And what you want to do is that you want to prove that your compiler is correct. And in order to do that, you have to define semantics for both your source language and also your target language. And then when your compiler translates a program P into a program Q, you need to show that these two programs are actually semantically equivalent. And this is something that people have done. There are compilers called certified C compilers. For example, there's CompCert. And they actually have a proof, and proof in this sense, that the compiler is correct. Okay, any other questions?
I have a question regarding a non-deterministic case. So, so the arrow star means it reaches some value, but what about for the non-deterministic case? So does it mean that there is some computation path that reaches the value, or does it mean that all computation path needs to reach the value?
It means there is some computation that does that, because if you go back to what an arrow means that we defined in the previous session, basically an arrow without the star just shows the possible transitions of the program, right? And then we defined the star as the transitive closure of the normal arrow. So when I write something like this, it means that program Q starting from valuation val can reach val prime. So there is some non-deterministic choice that reaches val prime. It's not that all of them should reach val prime. Okay, so we're going to finish today right on time. Have a good day and see you on Tuesday. Bye.